Okay, so here I just want to talk about something very small concerning transport of oxygen and delivery. Remember, we have to transport oxygen all the way from lungs to the tissues, and then we deliver it there. So this curve you're seeing right on this slide, it's what we refer as oxygen hemoglobin dissociation curve. So it's a curve that you can see it's simply a Cartesian plane. We have the x-axis and then we have the y-axis. The x-axis, we have what? The partial pressure of oxygen. Remember how we get the partial pressure of oxygen? We get it from, uh, it's actually 21% of the atmospheric pressure. That's the partial pressure of oxygen. So this partial pressure of oxygen you are seeing right here determines the saturation of oxygen on the hemoglobin. So that when we have low partial pressure of oxygen, we have low saturation levels of oxygen on the hemoglobin. You can see this part here, the low partial pressure, a low saturation level. Then when we increase at this tip region, we have the release, it's easy. This one is especially during exercise. And then we have the plateau region. The plateau region here, we have a partial pressure of 100. And at a partial pressure of 100, we have like fully saturated the hemoglobin with what? With oxygen. So remember, 1 gram of hemoglobin can carry up to a maximum of what? 1.34 mils of oxygen. So that simply is a simple description of what? Oxygen dissociation curve. The next thing that we need to discuss, it's actually the shift. So you can see these are three curves. We have one continuous line, black line. This is the normal. And then we have the dotted line on the left of the continuous line. Then we have also a dotted one on the right of continuous line. So this one on the right is what we usually refer as the right shift, the right shift. And then this one on the left is what we refer to as the left shift. So what has shifted? Whenever we say shift, what do we mean by shift? If you want to understand better the term shift, you have to determine the P50. So P50 is the partial pressure of oxygen when the hemoglobin is 50% saturated with oxygen. So you simply come to this y-axis and then you get the 50. So you see this is the 50 saturation levels of hemoglobin, 50% that is. So you move with that until at the point of interception. So if we are determining the P50 of the continuous line, you hit the black line and then drop with it, you get it somewhere 27. So the P50 of the continuous line is 27. And then you can also determine the P50 of the one on the right. So it will drop somewhere here, and then we drop with it. It comes somewhere 22, somewhere 22 there. And then you can also determine the P50 of the one on the right. It will drop you to somewhere 32. So the normal P50 is usually between 26 and 27. So if it's below 26, that is the left shift, and if it's above 27, that is the right shift. So what's the meaning of this? So how do we interpret? So you can see on the left shift, it means that the hemoglobin has high affinity of oxygen. It's so hard for the hemoglobin to actually release oxygen. It's so hard. It binds avidly to the oxygen. So that means it's actually during loading time, and this one usually happen mostly at the lungs level. So whenever the RBCs go to the pulmonary circulation to go and be oxygenated, usually like on the left shift, where there is avid affinity, where they bind avidly, oxygen bind avidly to the hemoglobin. So that's at the lung level. And then to the right, you can see the hemoglobin easily releases. It easily releases, it unloads. And how you can remember this is that a right shift, right, R for right, that R also can mean release or unloading. So right shift it usually means unloading of oxygen. And then left shift usually means loading of oxygen, so the affinity is actually high. So they can ask you, or some of the question is usually what are the factors that causes right shift. So one of the factor it's actually exercise. You can see here we have athletes running, and during exercise there's usually too much production of CO2 because the cells are metabolizing. There's usually too much production of hydrogen ions. There is usually increase in temperature. All these favors right shift because we want to deliver too much of oxygen to the tissue. Even though that explanation it's not very mechanistic, it's actually more of teleological. So the thing here is that right shift we need to release, we need to reduce the affinity of oxygen on the hemoglobin and favor the unloading or the releasing. So number one factor that favors this is CO2, too much production of CO2. Number two is hydrogen ion or acidosis. Number three, remember with acidosis, remember the RBCs, they usually only carry out glycolysis because they don't have mitochondria. So during glycolysis, we have this intermediate of glycolysis, we call it the 1,3-biphosphoglycerate. Then this 1,3-biphosphoglycerate, it's usually shunted away from forming the pyruvate and other stuff to forming 2,3-diphosphoglycerate with an enzyme we call the 1,3-biphosphoglycerate mutase enzyme. For those who have done good biochemistry, you know there's a Rappaport Lubering pathway or shunt that shunts away the intermediate of glycolysis into forming the 2,3-DPG. So whenever there's too much of hydrogen ions, it activates this mutase enzyme. Then the mutase enzyme increases the 2,3-DPG. And then the 2,3-DPG binds on the hemoglobin. As it binds on the hemoglobin, it favors release. So too much of this inside the RBCs favor the shift to the right, which favors release of oxygen to the tissues. And then, of course, temperature also favors the right shift. So if you are asked, just remember CO2, acidosis, increase in temperature, increase in 2,3-DPG will favor the right shift. Then the left shift, it's actually like a reverse of all these. So if there is low temperature, if there's low levels of hydrogen ions, if there's low level of CO2, if there's low level of hydrogen ions, it will shift to the left. And this one usually happens at the lung levels whenever oxygen is being loaded on the hemoglobin. Now, that having said, we have those that live in Mount Kenya. You can see this high altitude region where the atmospheric pressure is low. It's actually low, and this actually kind of cause the physiological anemia because we have more shift to the left because the partial pressure are low, the saturation levels are also low, but the affinity is also high. So high altitude, it will shift us to the left. Then there are those that live to Mombasa. These are the sea level. The atmospheric pressure is somewhere at 760. So we are fully saturated, and more to the right, so offloading of oxygen it's easy. That's why you don't need too much of RBCs, because there's too much of the partial pressure of oxygen. Then for the fetus, remember the fetus, they have fetal hemoglobin. So the fetal hemoglobin usually has it has a higher affinity of oxygen than adult hemoglobin. So the mother has the adult hemoglobin carrying oxygen and taking it to the placenta. Then the fetus has fetal hemoglobin. So the fetal hemoglobin has higher affinity of oxygen than the maternal hemoglobin. And this is something good because it helps in extraction of oxygen from maternal hemoglobin. So fetal hemoglobin is more shifted to the left. And then there's another thing that I need to talk about. This is the Aldini effect and the Bohr effect. So remember, at the lung levels, it's where we usually have the Aldini effect. And in this case, we have oxygen being loaded to the hemoglobin. But remember, as oxygen is being loaded, it displaces the hydrogen ions that are binding on the hemoglobin. So these RBCs also transport carbon dioxide. So the carbon dioxide that is transported, it's usually, of course, converted to bicarbonates, and then we have hydrogen ions. The hydrogen ions are buffered by hemoglobin, the protein. But at the lung levels, we have oxygen entering the RBCs, and it binds on hemoglobin. As it binds on hemoglobin, it displaces the hydrogen ion, which recombines with bicarbonate, therefore kicking out the carbon dioxide, and then we can expel it through the alveoli. Then the Bohr effect usually happens at the tissue level. So this simply means that at the tissue level we are producing too much of what? CO2. Then this CO2, of course, it needs to be transported all the way to the lungs. So as CO2 enters the RBCs, it's converted, of course, to the bicarbonates and hydrogen. Hydrogen binds on the hemoglobin, but this causes displacement of oxygen. So it causes oxygen to be delivered to the tissue. So entry of carbon dioxide at the tissue level causes delivery of oxygen. That's Bohr effect. And entry of oxygen into RBCs displaces hydrogen ion and therefore kicks out carbon dioxide. That's Aldini effect. So remember, they're not much related, but there's some mild relationship that you can always take it home. So basically, that's the oxygen dissociation curve that I have just presented in this single slide, all about delivery of oxygen in different circumstances. Thank you.